Okay, one of you shared this live stream on the WhatsApp group. Let's get started. Okay, so today we'll be doing the phenomenological Ginzburg-Landau theory. Before we go to the Ginzburg-Landau theory, let us say we start with the Landau theory of second order phase transition. We will see what Ginzburg had done later on. So let us start with Landau theory. How many of you know about the Landau theory of second order phase transition? Two participants. That's good. Okay. Rahul and Amit. Okay, that is good. Okay, we know that any phase transition normally is associated with an order parameter. Now, for example, you have if you have ice water transition, then this order parameter is density. If you have, let's say, a ferromagnet, then you have the order parameter which is the magnetization density, magnetization per unit volume. Now you know that these in a first order phase transition, you will have this order parameter. If I now describe this order parameter as something psi, then this order parameter at the phase transition undergoes an abrupt change. So this typically is a signature of first order phase transition. Of course, this is contingent to the fact that you have identified the order parameter of the phase transition correctly. So, for example, in ice water transition, the order parameter is the density. But if you take some other property, let's say opacity, that need not necessarily follow the property of a first order phase transition at the transition point, because that may not be the correct order parameter. So you have to, there is identifying the correct order parameter is not always easy. But in this case, let us assume that if I can identify the correct order parameter, then for a first order phase transition, the order parameter has an abrupt jump at the transition temperature, which I call Tc. In the case of, let's say, a second order phase transition, there is no abrupt jump, and at Tc I have this order parameter which has smoothly gone to 0. Okay. I'm a little perplexed here. Why don't I increase the page? All right, we'll see that. Okay, now what Landau said is this, that if I have a second order phase transition, then the order parameter has smoothly gone to 0. Now, one of the example of second order phase transition is most of the, so second order phase transition, it's most of the magnetic transition. Let's say ferromagnetic transition is often a second order phase transition. And here the magnetization is the order parameter. So I will just take M as a generic order parameter. It need not necessarily be magnetization. Because magnetization is a second order phase transition, I am taking M as my symbol for order parameter. So what Landau said is this, that I know that if I have, let's say, if I plot the free energy, which is a function of the order parameter, and if I plot that free energy as a function of M, and suppose it has some very strange sorry, it cannot be double valued, but other than that, it has some very strange landscape like this, then the physical value of this quantity will be the minimum of this order parameter, which means that the system will always, through the phase space excursion, will always come to the minimum of the order parameter. So if I do an experiment, this is always the physical value. This value, which I can call M star, this is the value that I will always measure. However, can I get this function, this free energy function, as a function of this hypothetical order parameter variation, if I can at least close to the minimum? So Landau said yes, I can, because since close to the phase transition, the close to a second order phase transition, M goes to 0, I can do a Taylor series expansion. So if I do a Taylor series expansion, I can have a constant, but we know that constant do not matter in energy. So I can always ignore the constant. Then I will do a Taylor series expansion and I will have various coefficients. Okay, now let us take a physical magnet. This expansion, I can do it anyway. I can always do such an expansion. When the order parameter is small enough, then I can do this Taylor series expansion. For example, then this alpha 1 will be del F, del M close to M star, And similarly, alpha 2 will be the double derivative. And so on and so forth. I will once close this OneNote window and open it, because I don't understand why I am unable to scroll down the page. Okay, now that's fine. All right, so and so on here. Now let us take a special situation, which is in the case of, let's say, a magnet. I am taking actually a ferromagnet. Now in such case, you know that if I have a ferromagnet like this, the magnetization suppose is pointing in this direction. The magnetization could actually point down also, or in any other direction. I can just take this, if this is a magnet, I can take this entire magnet and rotate it down. So if I rotate it down, then this whole thing will look like this. I'm not drawing it exactly. And the magnetization will point down. Now, if there is no magnetic field, just by rotating this piece up or down, I cannot change its free energy. Which means that the free energy cannot depend on M. Because then if I change M to minus M, it's the same thing. So changing just M to minus M cannot change the free energy, and any linear term therefore would have a problem of breaking this symmetry. Similarly,
Can you explain this once again, the physical argument?
can you see my video?
Yeah.
So suppose suppose this is your magnet.
Okay.
The magnetization is pointing up.
Yeah.
Now I can hold it like this, and the magnetization is pointing down.
Yes, sir.
Just by holding it up or holding it down, do I change the free energy of the system? I cannot. It's the same magnet. Doesn't depend
Yeah,
on
but
which.
the thing is that inverting the magnetization, if we are talking about the interacting system, then will it be the same?
This is a ferromagnet.
Yeah.
It's an interacting system.
Yeah, so the inversion of spin will change the JSI dot S.
Wait. Don't go into jargons. I am holding, this is an interacting system, this is a ferromagnet.
Okay.
I am now holding it downwards. Have I rotated all the spin downwards?
Oh, okay. I got that.
Okay. Think simple. Don't go into. Life is normally much simpler than what you imagine it to be. Okay, so therefore all the odd terms would disappear. And then I know also the constant, I don't need to bother about it. So that constant is something that I can choose my origin anywhere. So I will write my free energy as this. It will have the square term and the quartic term. Now remember, this is for a magnet specifically. If I had taken ice-water transition where there is density, then of course there is no reason why the cubic term should disappear. In fact, density has another constant, it cannot be negative. So it is always positive. But for a density, there is no reason why uh, I should drop all this cubic.
Another thing, can I ask that can we choose anything as a order as an order parameter for any kind of system? Because I thought that there is something symmetry breaking is related with the order parameter.
Exactly.
Unless that is guaranteed, we can't choose anything as my order parameter.
You no, you cannot choose anything as your order parameter. Okay. So you have so however, so you have to the order parameter has to be related with the symmetry that you are breaking. Okay. So
Yeah,
for example,
that must be expressed by the the variation of the order parameter.
that must be expressed in
Expressed, I mean that must be reflected in the variation of the order
yes,
parameter.
that is right. That is right. So for
So
example, if you are taking magnetization, then the fact that you are in a ferromagnet, the fact that your rotational symmetry is destroyed below the transition is something that is reflected by the magnetization.
yeah, yeah. So the question is that can we take anything else apart from the magnetization as my order parameter in the case of ferromagnetism?
You can take something related to magnetization as the order parameter, you could, but you cannot take anything. For example, can you take, let's say, the color of the object as the order parameter? No, because if you go across the ferromagnetic transition
Yeah.
and you take the color at optical frequencies, there is no change in color.
Okay. Okay.
Can you
Okay.
take the reflectivity? No, you cannot. There are things that change at the transition, but still they do not reflect the broken symmetry. For example, can you take the electrical resistance? You know that when you have a transition, typically in a ferromagnet, if it's a metallic ferromagnet, then because you are suddenly going into an ordered state, your spin scattering decreases. So you have normally a reasonably larger decrease. You get this kink and a larger decrease of the resistance below the ferromagnetic transition.
Yeah. Yeah.
But can you take resistance as the order parameter? No, you cannot. Because for resistance, you can never take as the order parameter because it's not even a thermodynamic quantity. Resistance is a dynamical quantity. It's the response to an electric field. So you cannot do thermodynamics with resistance. So resistance is ruled out as an order parameter. As you will see later on, there is in some cases finding the correct order parameter may be difficult. For example, in a superconductor, what is the order parameter? It's very non-trivial. You could say, for example, I will take the diamagnetic response as the order parameter. But the diamagnetic response is not the order parameter in a superconductor because that is not the symmetry that is broken. The diamagnetic response is coming when you are applying a magnetic field. Now, when you are applying a magnetic field, you are already destroying the symmetry of space. So that is no longer a spontaneous symmetry breaking. Unlike a
Okay.
ferromagnet,
Sir, can you say this thing in that fashion that this is also an response factor that is we are bothered about.
which
So
one? Which one?
the magnetic response is just like an resistance that the is a dynamical factor.
The magnetization.
Because the magnetization is the field is repelled when the field is repelled when the field is applied, right? So the
Field is repelled. No, no. Are you talking of a magnet?
No, no, no. I am talking about the superconducting states properties, right?
Yeah, so in a superconducting state, the magnetization is something that is, it, it is not just a response function. See, magnetization in the presence of a magnetic field is a thermodynamic quantity, okay,
Okay.
like pressure. So, therefore, magnetization
Oh, I
could,
got the
in
point. Oh,
principle,
okay.
have is also, it can be a state variable. So,
Yeah, yeah, yeah.
since H is a state variable, you can have magnetization as an order parameter. But the problem is elsewhere. In a ferromagnet, the, you have a spontaneous magnetization, and the spontaneous magnetization means that you have no applied magnetic field, but the symmetry of space gets broken by this magnetization.
Yeah, yeah, yeah.
In a superconductor, you don't have a spontaneous magnetization. You have only an induced diamagnetism. Now, when
Yes.
you are inducing the diamagnetism, you are applying a magnetic field. The moment you have applied a magnetic field, you have broken the symmetry of space already.
Yeah.
Then
Yeah.
now, if you get a magnetic response, that is no longer a spontaneous symmetry breaking. It's an induced symmetry breaking. And
Okay.
induced symmetry breaking does not imply a phase transition. For example, if you take a paramagnet which has no order and you
Yeah.
apply a very large magnetic field, all the spins will get aligned in the direction of the field.
Yeah.
That is not a phase transition.
Oh, okay, sir. Okay, I got the point. Okay.
All right. Okay. So now, if this is the form, and then of course I will have it doesn't end here. I will have, let's say, the next even term and so on to 6, 8, and so on. But what Landau showed is that if I keep it minimally up to the quartic term, I can reproduce a second order phase transition. How is that? So I have to find the minima of this free energy. So let's take del F del M. And if I take del F del M, I will get base plus twice beta M cube equal to 0. This is the condition. And therefore, this is M into twice alpha plus twice beta M square equal to 0. So I get two solutions here. Either magnetization is 0 or magnetization square is minus alpha by beta. Okay. Now, when do I get these two solutions? You have to find out which solution is a stable solution. So, you take del square f del m square, and that is twice alpha plus 6. Yeah, sorry. Yeah, that's right. 6 beta m square. And then you see that if you have, let me see. So let's suppose now, let me take this solution, m equal to 0. So this is my solution, and then del square f del m square equals to twice alpha, and this has to be less than 0 if this has to be a minima. On the other hand, let's take the other solution. this is minus 4 alpha. So therefore, you can see it depends on the value of alpha whether this quantity will be, if alpha is positive, then this is positive and this is negative. On the other hand, if alpha is negative, this is positive. So depending on the value of alpha, you will have either this state, which is the stable state, or this state, which is the stable state. Now, the point is you want to mimic a system which will undergo a second order phase transition. So Landau's prescription is that the simplest thing you can do is you take alpha, which is some constant, and now A is a positive constant, and T minus Tc. Alright? Now you see for T less than Tc, alpha becomes negative. Okay, here this is misleading, I should remove that. No, is that correct? Yes. Right. Yeah, so sorry. For T less than Tc, alpha is negative. So therefore, my solution will be given by this one. Which means that I have a finite spontaneous magnetization. For T greater than Tc, alpha is positive. So now my solution is m equal to 0. Okay. Now this appears extremely trivial, and it is actually extremely trivial. But the point to note is that this free energy ansatz, right now it's an ansatz because it's just a guess. This is the minimal ansatz that reproduces a second order phase transition. All right. Now, what you can go back and you can take this minimal ansatz, and now you have the temperature dependence, which is entirely in the first term. You can try to calculate specific heat. You know that for a second order phase transition, the specific will have a finite jump at Tc. You can calculate the entropy. All of this, you will see this is consistent with a second order phase transition. Now, if you remember our introductory lectures in superconductivity, where we had done the thermodynamics of the superconductor, we know that the superconducting transition is a second order phase transition. So then Ginsburg and Landau went on to set up the free energy functional now for a superconductor. Now, first is what is the order parameter? Now, this is non-trivial because the superconducting transition is a very strange transition. what does it actually break? It was not clear for quite a while on what is actually getting broken in a superconducting transition. And later people realized that what is actually getting broken is this symmetry. If you take, let's say, a metal, then you have a phase symmetry. The phase symmetry means that each of these electrons in a metal they undergo collisions, and at every collision their quantum mechanical phase gets scrambled, it gets changed. So therefore, this is what is often known as the random phase approximation in a metal. That since the phase of the electron is varying over very short time scale, which is of the order of the scattering time, you don't need to consider the phase of the electron at all. So in a metal, interference effects are practically not there. But in a superconductor, you have already shown that all the Cooper pairs get into one phase. And this phase rigidity, the consequence is twofold. So this phase rigidity means you are starting from a situation in the normal state where the average phase was 0. Average phase is 0. This is the normal state. And then in the superconducting state, ground state, all of them are locked at some value theta. So definitely this is one quantity. The phase is one quantity that changes between a superconducting state and a normal state. But then Ginsberg and Landau went one step ahead and they said that it cannot be just the phase. There has to also be an amplitude, because you know that the superconductivity is binding of the Cooper pair, and there is a binding energy. There is a binding energy of Cooper pair, and this binding energy is delta. So therefore, in principle, the superconductivity can get destroyed if all these Cooper pairs had become phase incoherent, if the phase is scrambled. But it can also get destroyed if you actually break the Cooper pair. So both these effects, they said, will be phenomenologically captured in an order parameter that will look like this. Now this is the amplitude of the order parameter, and this is, so the order parameter is actually a complex quantity. This is the amplitude, and here I have the phase. They also said, okay, we'll see later on how one can connect the amplitude. What physical quantity we can connect the amplitude to. Okay, so again, just like in a magnet, the free energy of the magnet does not depend on whether I am holding the magnet like this or I am holding the magnet like this or any other orientation. For the superconductor, when you calculated from the BCS ground state variationally that all the Cooper pairs have the same phase, you did not find any absolute value of the phase. The phase could have been anything. Just like the magnetization can point in any direction, the phase for the superconductor, for a given superconductor, can be anything. But it has to, whatever it is, it has to be same for all the Cooper pairs. You cannot have this to be theta here and theta 1 here. Everything is theta, but then this theta could be what it is, it's indeterminate. Which means that for an isolated superconductor, this is very important, for an isolated superconductor, the free energy cannot depend on theta. So therefore they said that the free energy in the simplest, or if you want the free energy density rather, I should not write this as the free energy density. So I am writing small f, and remember small f is the free energy density, will be some constant plus alpha and alpha as usual is A P minus Tc. Okay, now this will immediately give me a solution again, which is the same as what I had gotten for a magnet, but that is no big deal. So it is, this is 0 for T greater than Tc, and then psi mod is equal to minus A for T less than Tc. Okay, but then what else do I do with it? This is no big deal. There comes the contribution of Ginsburg. So this was Ginsburg's primary contribution here. Landau has actually already developed the Landau theory of second order phase transition, which is what I described to you before. But Ginsburg added this quantity, which made it enormously more powerful. So first, before we go to the Ginsburg-Landau term, let me first write the free energy as such. I have written the free energy density. So the free energy would be, let's say, a constant, which is the free energy of the normal state, plus Fn is a constant. Anyway, it doesn't really matter, but and I am assuming here that this could be in principle a position of a function of the position. So if I integrate over the volume, I get the total free energy of the superconductor. Now what Ginsburg said is this: how does theta come in this expression? The theta would come in this way. What if you have a non-uniform superconductor, which means that you have the whole superconductor, the order parameter is not homogeneous, but it is, you have either twist in the phase, twist in theta, or you have twists in the amplitude. Now, twist in the amplitude, as you will see later on, is much more difficult to get for U1 symmetry, because that's a gap mode that is actually equivalent to the Higgs mode, but we'll come to it later on. So the important point is that what if you have inhomogeneities? Now you know that in a magnet, if I had, let's say, the spins which were not in the ferromagnetic state, if they were not parallel to each other, but they were at an angle to each other, this would cost me energy. It will be a higher energy state. So Ginsberg said in a superconductor also, the inhomogeneity of the order parameter should also produce a free energy increase. Therefore, he said that in addition to these terms, the free energy density should have a gradient term. The gradient term would be proportional to the gradient mod square of this order parameter, and then the next part which he did is not something that is necessarily rigorous. It was essentially purely a dimensional analysis. Now, the point is, you can ask me how he got this idea. The point is that he was doing simply the dimensional analysis, and this is why Ginsburg-Landau theory was for a long time considered to be just a phenomenology that works but that does not have any fundamental value. Because you see, everywhere you have this kind of constant, alpha, beta, which you do not know. Like in BCS theory, you have every parameter that you can calculate out. Here you cannot calculate. So now, of course, thanks to the work of Gorkov, we know that from BCS theory we can derive Ginsburg-Landau theory, and when you derive Ginsburg-Landau theory from BCS theory, all these alpha, beta, you can derive them exactly. But that is not how Ginsburg and Landau had done their work. When they did not know that how to calculate these prefactors, and they said that okay, we'll develop free energy, we'll calculate quantities, and then we'll take inputs from experiments and fix these parameters. So we go back to the original approach of Ginsburg and Landau, and let's try to see what they did with the gradient term. So Ginsburg said that this term does not have the dimension of energy. So to have a dimension of energy, I will multiply this with h cross square by 2m, taking inspiration from quantum mechanics. Now, don't ask me to derive this. This is not a derived expression. This was just from hunch. So in Ginsburg-Landau theory, the proof of the pudding is in the eating. So we will see what we get eventually out of Ginsburg-Landau theory. So that means that the total free energy or the gradient term would be when you integrate it over volume. Okay, this is the gradient term, and then what Ginsburg did was even more. He said that okay, I am using h cross square by 2m, taking inspiration from quantum mechanics. Then let me try to push this analogy even further. So I know that if I have a momentum in zero field, in the presence of a magnetic field, this becomes E star. E star is just the charge. It's because I will have a Cooper pair with 2E. So you can say E star is 2E. Initially, you just leave it at E star. So then he said we know this. This is of course not just quantum mechanics, it's electrodynamics. And then let me use the quantum mechanics analogy and say that my P is H cross by I grad. In the presence of a magnetic field, the grad will be replaced by grad minus I E star by H cross C into A. And therefore, he said that the gradient term will take care both non-uniformity of the order parameter and magnetic field. And in fact, the non-uniformity of the order parameter and the magnetic field would couple. So now I replace my gradient with okay, and finally you have also the magnetic field energy. And that magnetic field energy will give me the magnetic, purely the magnetic field component of the free energy term. All right. So this actually accounts for all the components of the free energy.
Sir,
So to
will you explain the importance for involving a term like grad psi once again?
that Shai is inspired from this fact that you take the ground state of the superconductor, you know that the variationally minimized state has the same phase everywhere. Okay? So
Okay.
suppose the phase was not the same everywhere. If the variationally minimized state is with the phase same everywhere, that means that if the phase has a gradient, then that would cost an energy. It would be a higher energy state.
Yeah, yeah.
Okay, that is the reason why I am putting this term in the free energy. Think in terms of magnets. In a ferromagnet, this is the state where this is the lowest energy state. But if I had a state where each spin, and this is actually what happens when you excite spin waves, each spin is slightly tilted with each other. This is a higher energy state. This is an excited state.
Okay.
Okay. And this excited state will have an energy that is higher than the ground state, and you can express that here in terms of the gradient of magnetization vector.
Yeah, yeah.
Uh, all right.
Yes, sir. Yes, sir. And
So
sir,
now you consider these to be in a superconductor. Take some universal axis. The way to visualize this is the following. Take some universal axis. This is some universal axis. It can be arbitrary. And this is my angle theta. Okay. So the lowest energy state is theta constant for theta is a constant. But here theta becomes a function of r, and this state, of course, is not the variationally minimized state, so therefore it will cost you energy. That energy is accounted for by this.
But sir, from variational principle, we get a criteria for phase correlation. So will these be valid for the excited states?
Will this be valid? What will be valid for the excited state?
The phase correlation, because we are seeing that phase is continuously changing. So will it be a superconducting state at all?
We'll see. You can always create an excited state. Can you take a magnet and twist the spins?
No, because here we are seeing that in these diagram that you have drawn, the average M is getting zero, so it's no longer a ferromagnetic state within this region. The spins are up and down continuously changing. So from
Yeah, that
these,
is, well, the point is, okay, let me ask you this, because these analogies will not make sense if you, have you studied spin waves?
what's sir?
Have you studied spin wave in ferromagnet?
No, 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 no.
Okay. Now, that is, so let me see which book has it, and you should quickly read that, because when you, let's say, a ferromagnetic state in the, at zero, t equal to 0, everything is, at t equal to 0, you have everything which is parallel to each other. When you
Okay.
increase temperature, what happens? How does
This,
magnetization decrease as you increase temperature?
yeah, the spins are the domain walls interacted with each other, and
No, no,
it's
no, there is no question of domain wall. Don't get confused. In a ferromagnet, the spontaneous magnetization, how does it decrease with increasing temperature? Forget domain. Ideal ferromagnet does not have domain. Domain is a different thing. Spontaneous magnetization, how does it decrease? But this, I think there is a, you have to study this somewhere, otherwise you will never appreciate this. And I don't think I should start teaching ferromagnetic spin waves here, because okay, excellent. You can take any book. So this is applicable to all of you. Read spin wave in ferromagnets to understand. So you have spontaneous magnetization. The spontaneous magnetization, don't get confused with domains. Spontaneous magnetization is the magnetization inside a domain. That has nothing to do with the existence of domains at all. Whether you have domains, whether you don't have domains, the spontaneous magnetization in a ferromagnet remains the same. So the spontaneous magnetization decreases, and then at Tc goes to 0. Why does it decrease here? This entire place, this entire temperature range below Tc, it is a ferromagnet. Yet this corresponds to all the spins parallel. What does this correspond to? Why has the magnetization decreased here by this much? Okay, So this is, if you read from Ali Omar, Solid State Physics, page 483, and alternatively, you can also read the book of Kittel, and Kittel also has spin wave. In rather great detail. So this, I am drawing it here in this form because I cannot draw it in 3D. Actually, what happens is that it does not go this speed. When you have a spin wave excited, each of the adjacent spin has an angle with it, but it actually does not go all the way in the other direction. It is more like it goes in this, it has a precession like this. So it goes like this and then again goes up. But effectively, so you still have a net magnetization which is non-zero, but the overall magnetization gets reduced. Okay, I suggest you all read this part. Okay, what I wanted to just do at the end is to write the full free energy expression. There is a constant, then I will have first the Landau terms, then I will have the Ginzburg term, that's how this becomes Ginzburg-Landau theory. And then finally I have the magnetic term. Okay, good. I got the full free energy functional. So what is the next job? The next job is to minimize it. But I have to minimize the free energy. But I have to minimize it not with respect to a parameter, but I have to minimize it with respect to phi of r, which is not a number, but it's itself a function. So I don't know, maybe some of you are aware of this. What you have to do is what is called functional variation. Where you take the functional derivative of f with respect to this function psi of r, either psi of r or psi star of r, and then you find the radiationally minimized state of the superconductor. So actually, you have to do a functional variation with respect to 5 variables. One is psi of r, then psi star of r, this is the second quantity. Then you have magnetic field, so you have to do a variation with respect to A, which means that A vector, which is AX, AY, AZ. You will see that out of these, the variation with respect to psi and variation with respect to psi star will just give you the same thing except the complex conjugate of each other. So it's an equation, you will get the same equation and its complex conjugate. So you can do just one of them. And the variation with respect to the vector potential will give you the expression for calculating currents in a superconductor. Okay, so I'll stop here and we'll continue again on Friday, I think. Yeah, we'll continue again on Friday. Okay, any other questions?
Yes, sir. One thing is that in the in the case of free energy h cut square by grad psi square, you have told that the h cut square by 2m factor is from dimensional analysis,
Yeah.
right? But I am thinking that we can say it from the Hamilton-Jacobi theory, because there we have the p square by 2m is my energy factor. So in the case of in the case of Hamilton, in the case of classical mechanics, p is something dq dx, right? So the from the Hamilton's equation of motion. So there we can say, putting my generalized coordinate as psi, we can create the energy term as h cut square, not grad square, rather grad psi square. As
Yeah, that's not entirely incorrect, except for one thing. The problem is that the psi here, which I have defined as the order parameter, it is a wave function like object, but it's not a quantum mechanical wave function. So if psi was a quantum mechanical wave function, then this argument that you are giving would have gone through exactly. Here it is an object, it is an order parameter as I have defined it, but this order parameter is inspired by the quantum mechanical wave function. And therefore, when I am putting this h square by 2m, I am pretending that psi r is actually a wave function. That is where the analogy and the inexactness, the qualitative nature, rather, it's not the inexactness, it's the qualitative nature of the argument comes in there.
okay, sir. Okay.
If this was the wave function that one is dealing with,
Yeah.
what you are saying is correct.
Yeah, yeah, yeah. I got that.
Okay. In fact, you will see in the next class, when we variationally minimize it, we will get something which is very close to the Schrodinger equation. But it will not be the Schrodinger equation because of actually this term over here. We will get a nonlinear term. And that nonlinear term is absolutely important to get any phase transition. So it is, this whole formalism takes inspiration from quantum mechanics, but this is not quantum mechanics per se.
Okay, sir. And another thing, what you were saying, I missed the point, that is Higgs mode or something like that.
Yes. So Higgs mode is something I will explain to you. Okay, I can tell you very briefly straight away. So
Basically, because I am asking that I know the fact that in case of where we are where we are minimizing the potential or something like that. We have massless states and we are call them Goldstone modes, but the Higgs modes are where the mass is picked up. I can't find any mass term here.
Okay, so actually one can even use shy or whichever you want. So now you can try to plot this above Tc. So this is my free energy. Now this axis is, let's say, psi. So above Tc it is like this. So psi is 0. I have no superconductivity. Below Tc, this is how it is. Okay. Now
Yes.
this is slightly misleading because I know that I have to plot not with psi mod square, so not psi mod, but with psi. That is my order parameter. And psi has also theta in it. So now let me put another, let me take this a plane, and then I can define that the radial distance is proportional to this. The radial distance is proportional to this, and the angle here, this is theta. So in that case, how
Yeah.
will my free energy look like?
Yeah. So
Let
instead of it will take a bowl like shape.
wait, we can wait a minute. What are you seeing on the screen? It will take a shape like this.
Yeah. Yeah. Yeah.
Okay. I have opened it partially. I am not showing you the full thing,
Yeah.
but it will look like this. Now, there are two kinds of. Now I cannot increase this. Let me see if I can. Okay, now there are two kinds of modes that you can excite. One of the mode is this azimuthally, the
Yeah.
other mode is radially.
Yeah.
Now,
As
this
you.
azimuthal mode,
Yeah.
you can excite it essentially with zero energy.
Yeah. Goldstone modes. These are.
That's a Goldstone mode.
Yeah.
But the radial mode, it's like a particle in a harmonic potential well. And you know that harmonic potential well has a 0 point energy. So there is a minimum energy threshold. That is the mode, that's a Higgs mode. It's a gapped mode. And in fact, this that's the mode that is, it's called the Higgs or the amplitude mode. In high
Yeah,
energy, it's
one
called the
thing that
Higgs
I
mode.
need to clarify that uh, I have seen in in the particle physics that Higgs mode is something related to the local that when we demand the local invariance of phase, the local phase invariance mm, of the theory. But here we can't find anything like that, and we are saying that
See, the Higgs mode, when you have a symmetry breaking of this kind, the Higgs
yeah,
mode is essentially just the orthogonal mode to this Goldstone mode. It's this amplitude mode here.
okay. So I think I have some wrong notion. I think.
Okay. So what means in the high energy context, I know that this is the only definition of the Higgs mode. But in the
Okay.
high energy context, how it is defined, whether there is some definition, as you say, with
Yeah, local invariance. The local gauge invariance is the origin of Higgs mode.
local what invariance?
Local gauge invariance of the theory.
Local gauge invariance.
Yeah.
Okay, I don't really understand what the local gauge invariance is. That I think probably what you are talking of is the interaction of the Higgs mode with the Goldstone mode, which provides the mass to particles.
Yeah, basically I'm saying that when I have demanding I demanding the local gauge invariance of the theory, I am invoking some gauge fields in the theory. And as I have in case say if we are talking about the photons or something like that, if I have 4 degree of freedom, then three the massless particles become massive, and the thing and another basically 2 2 distribution becomes 3 3 1 distribution, and that is coming from Higgs modes.
Yeah, that's see that is fine. So, but the mode itself is actually the amplitude of the order parameter. How
Okay.
then that interacts locally is that's a question that is more intricate. That's what you are telling me here. But in terms of the mode itself, it's a Goldstone and the Higgs are the two orthogonal modes that
Okay.
really don't mix with each other unless you have other mechanism to mix it. So, for example, these two modes in a clean superconductor will not mix. They are orthogonal modes. But
Okay.
if you have, let's say, disorder and k is no longer a good wave vector, sorry,
Okay.
good k is no longer a good quantum number, then you can mix the Higgs and the amplitude mode, sorry, the Higgs and the Goldstone mode. So then the two will get hybridized, and then you will not be able to differentiate really between the two. They will not remain orthogonal.
Okay. 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 Yes. Okay. Got it.
All right.
Thank you.
So let us stop here and we'll meet again on Friday.